and set the secure level to -1, which is more convenient. And just to show the implementation of the arbitrary shell commands, we grep for root in the master password file and store it in a file in the temp directory. We then create a new connect back shell to check the changes on the target machine. And check for the file in the temp directory. That's it, job done. And, well, since we are nice people, we uninstall it as well. Okay, actually the movie continues to show that all the other releases works as well, but we don't want to see that now. So, Joel, can you please take care of your laptop? Thanks. Over to my friend Carl, which is going to talk about some other stuff.
Hello. Hello, my name is Carl. I'm going to talk about a kernel exploit for a vulnerability in FreeBSD 6.0. This is a vulnerability in the wireless subsystem of FreeBSD. This was found by me in mid-2005, and then it was also released update to fix this. First of all, I'm going to talk a little bit about auditing the code, and then later on the implementation of the exploit. First of all, the wireless subsystem in FreeBSD, the code is relatively new. The wireless code has a pretty complex link layer protocol, and there were some obstacles that I came across while auditing this code. First of all, the code is not written to be easily read, at not least for me. It contains some huge switch statements and tricky macros and those sorts of things that make it hard for an auditor. And the management layer for the wireless protocol, it is unauthenticated and unencrypted, which makes it pretty convenient for a malicious person. And while I was auditing this code, I found a local issue, IOCTL, which it was possible to retrieve some kernel memory. We disclosed some kernel memory. That was interesting, but while I was continuing looking, I found something more interesting. That was another IOCTL, and that IOCTL is the IOCTL which returned the access points in the vicinity. And this is called after a prior scan. And here is some of the code that implement that. And we're going to have a little bit of a look into this code. And the union U here is a local stack variable. This is used by the kernel to construct a portion of data that is later on copied out to user space. And this is the loop which iterate over all the access points that the kernel has in a list that it is knowledgeable about. And first of all, it calls a function, you see there, get scan result. And this function, it calculates the amount of memory needed for some dynamic-sized fields attached to these access points. And then it later on copy out those dynamic sized fields to this temporary buffer that we talked about earlier, the union U. And to dive into this, we will look a little bit further into this get scan result function. And this function, as I said, calculates the length, the size of these dynamic fields, and these fields are the SSID, and it is the VME and the VPA and the VMI. And the VMI and the VPA can both have a length of 255 bytes, and the SSID is constrained to 32 bytes. And if you see there, there is a variable called ISR IELN. This is the length of the two biggest dynamic fields here. And they are added together and then added together to the total length of those dynamic fields. There is, however, a problem here. The ISR IELN is declared as an unsigned 8-bit integer. And as you might notice, if you have those two fields, and if they have a sum that is larger than that 255, that is the maximum value of this unsigned int 8-bit, then we have a problem. And that could probably, or it can be used by the malicious user. And now we want to test our theories and see if it is possible for us to do something useful with this. So what we do is to hard-code a test case into the kernel, and we create a custom kernel with debugging support with GDB and DDB. And Christer, he talked earlier about it, so I think you are pretty familiar with that. And then we want to enable the GDB as the current debugger. And we trigger the affected code path. In this case, we just issue a ifconfig with the scan command. This will call this IOCTL, which was vulnerable. And here is the output of the DDB when this panic was occurring, because we had a page fault within the kernel, so we had some problems here. And if we look at the virtual address here, we see that it is 41, 41, 41, 55. And we provided some data here with a lot of capital A's, which is 41 hexadecimal. So we see that we can control the some of the values here. And we want to investigate this a little bit further, and we want something better than the DDB here. To go a little bit deeper into this, we want GDB. But first of all, we want to ask us the question, can this be triggered remotely? Because that would be much more interesting. Because ifconfig from a local machine is not very useful. And as a matter of fact, there is an application called VPA supplicant, and this is regularly calling this IOCTL while scanning for access points in the vicinity. And this application, VPA supplicant, it is needed to authenticate to any access point, providing better encryption than WEP on FreeBSD. So if you have an access pointer with high encryption, then you are probably running VPA supplicant. So, now we want to construct the malicious frame that make this happen. And to do that, I've modified NetBSD, so I was able to send arbitrary raw frames from NetBSD with the BPF device. And as I said earlier, we want to switch to a better debugging environment, GDB. And now we introduce another computer. We introduce a debugger machine, and this is attached to the target machine with a serial cable. And then we configure the target machine so it will enable this GDB. And here is the beacon frame sent in there to the target. And we drop into GDB on the debugger machine here. And now we have the source code, so it's much easier for us to investigate this problem. And if we look here, the IREC was a local variable, so we have clearly overwritten a local stack variable. And if we look at the backtrace, we have also overwritten some frames further up. Oops. And here is a dump of the local variable u, which was the big union that was the temporal buffer that the kernel copied into before copying out to user space. And if you see all the red here, and that's the capital A's, our supply data. And if we look at the frame pointer here, we see that it is in the middle of this. So we have clearly overwritten the saved return address and all that stuff. So now we have a good position here to do something useful here, to develop an exploit here. And what we want to do here is to find a suitable value to put there as the return address. And we can't rely on stack variables, stack addresses, as it is very unpredictable for us, especially as we are exploiting this remotely. So what we need to do here is to, or what I did, was to search the kernel image for a generic kernel, and I searched it for an instruction which makes it possible for us to resume the execution. So, for example, if we have this instruction jump ESP, we will have the execution resumed after our overwritten saved return address. And here is just a small script, and this will search for suitable byte sequences, and the FFEF is one of those. And this was actually found in the generic kernel here, so I could use this one. So now we have the possibility to execute our code within the kernel space, and now we need to figure something out. We need to figure out what to put here. And this initial payload is pretty limited. First of all, it can't be too large, because if we make it too large, it will overwrite another frame further up that we really want to have intact, because we want to resume the execution after we are done. Because we don't want the caller of the IOCTL to completely fail here. So if we limit this to 32 bytes, we will be okay. So this initial state 1 payload is 32 bytes in my exploit here. And what it does is to locate a second stage payload here. And this code, it will traverse some kernel lists, locate that second stage payload, and then jump to it. Nothing more than that. And the second stage payload, it is responsible to do the actual installation of this backdoor. So what this has to do is to allocate memory for this backdoor. It will copy some back